Okay, good afternoon. Welcome to review time. So I'm recording this for the YouTube channel as well, so if you want to participate in office hours that way, you can. If you want me to do a problem during office hours on Thursday, send me an email, and even if you can't make it, I'll do the problem in office hours. So what I'm hoping is that this review can be somewhat student driven in the terms of what kind of content you want to see. So a good thing to do for the review for today, tomorrow, Thursday, and then also office hours on Thursday would be to, while you're in your study mode, studying problems from chapters 1, 2, 3, 4, 5, come across a problem that stumps you, write it down, and then we'll work on it in class. And I can probably give you a better explanation, or not in class, but in our reviews or whatever. And then I can probably give you a better explanation than can the help me solve this button on Pearson. So, with that in mind, does anyone have any topics that they want to discuss?
Okay. Can you do converting from standard to vertex form? Like the completing the square thing?
Sure. Completing the square. Do you know what chapter that's from? 2.1. Let's see if I can
Yeah,
find it.
that's why I wrote it down, because I was like, I have not done that.
Yeah, that's a good one. Let's see. Preview. No, let's not do that one. Okay, let's try this one. Yeah. Okay, well, there's two ways you could do this. Okay, let's just write it down. And then convert to vertex form. Okay, so for something like this, there's a couple different options that you can do. You can complete the square, or for something like this, you could even use a second method. So I'll show you method number 1, which is completing the square. So method 1, complete square. How do we do that again? Do you remember? Sorry?
No. I know it's like a fraction thing.
Yeah, some kind of fraction thing. So if you have ax squared plus bx plus c, it's got to have to do with this b value, right? You remember what we do to it? Yeah, you put it over 2 and then something else. Square it. Okay, so b over 2, quantity squared. It, for our case, is 6 over 2 squared, which is 9. 6 divided by 2 is 3. 3 times 3 is 9. So this tells us what is the magical number, which we need to then do something with this number. What is it that we need to do?
Add it and subtract it.
Yes, you need to add it and subtract it. Why not just add it?
It's changing the...
Exactly. It would change the output. It would change the expression. We want to have the same expression. If I add 9 and then subtract 9, I'm right back where I started, right? That's the whole goal, is to be back where I started. So now we notice that I can do something nice if I just restrict my attention to the first 3 terms, right? I can factor this. And in fact, it's going to factor as x plus 3 times x plus 3, or x plus 3 squared. Yes? Okay, so what was the point of that? Well, we chose 9 specifically so that when we got to this part and we want to factor, we want to think of a number that if I multiply it, two numbers, if I multiply them together, I get 9. If I add them together, I get 6. It's 3 and 3 that I'm looking for, right? And the whole reason that I chose 9 was because I know that if I take the middle term, the middle b value, divide it by 2 and square it, I'll get a number which will be a number so that its square root is 3, right? Or its square root is like half of the b value, right? So that if you add it to itself, you get the b value. And if you multiply it with itself, you get this number which we specifically chose to add and subtract. So this tells us that the vertex is where? How about the y value? What's the y value of the vertex? Yeah, -9. Okay. You want to take a quiz?
Mm-hmm.
Okay.
I'm staying here.
Yeah. Which one are you doing again?
I think it's quiz 6. It's like 4.2, 4.4. Unit circle. Is it hard? I think it, right?
It was so long ago. I don't even know what quiz even. Was that the most recent one?
Nah, well, yeah, it would be the most recent one. Before the exam.
Still don't
Or was
remember.
it before the exam?
That's not gonna help. That's not helping.
Okay.
me.
Have you seen any part of this
No.
quiz?
I
Have you
don't
communicated
remember.
with anyone
Sorry,
about
sorry.
it?
Square? Would that make you trust
Did you pinky promise me? Okay, you gotta do the thing with the thumb, dude. There you go. Now you sealed the pinky promise. Okay.
So,
Good luck. You can just go in the back there.
appreciate it.
Okay, so what you got to remember is, okay, maybe one thing that would help you to remember what is the x value of this going to be, which I think probably you're sitting there thinking like, it's either 3 or -3. Am I right?
Isn't it
It's
negative?
a negative.
It's going to be -3, but here's how you can remember if you forget. Like, okay, if you remember that it's x minus h squared plus k, okay, then sure, you can say, oh yes, it should be -3, right? But what I'd rather you do is remember the theory of transformations, right? Say I have f of x, right? Okay? If you add something on the inside, so plus a, okay, right? If you add something on the inside, then this is going to have a transformation which is going to be a horizontal shift to the left, right? To the left. So the x value, which is 3 to the left of 0, is -3. So that's why this should be -3. Okay, because this is a transformation of x squared, right? You transform it into this. You take the function x squared, you move it 3 to the left and 9 down, right? If you take the vertex was at 0, 0, move it 3 to the left and 9 down, then you're at the point -3, -9, okay? So, just remember that these transformations will basically, help you to understand, like, what's going on here, okay? Anytime that we are in the inside of these parentheses, you got to remember we're in, like, upside down world, okay? Mermaid Man set his belt to Wumbo, okay? And we got to go the opposite of what we think is going to happen. So that's that. Let me show you another way that you could have done this. You could have said, well, x squared minus 6 is x times x plus 6, right? If you set that equal to 0, then you know that the zeros will be x equals 0. Oh, wait. Sorry. Yeah, x equals 0 and x equals -6, right? Those will be the zeros. So, if you have a parabola, okay, if you have a parabola whose zeros are -6 and 0, the vertex will be halfway in between the zeros. So you know that the vertex has to have the x value -3. And so then if you wanted to know, well, what is the y value of the vertex? All you have to do is, look, this is a point on the parabola. You know its x value. You can find out the y value by plugging in the x into the equation, right? So that would be -3 quantity squared plus 6 times -3, okay? So then this is 9 plus -18, which is -9, which tells you that this is -9, okay? Two different ways to do the problem. Okay, well, and I guess if it says convert to vertex form, then you need to write it in vertex form. But if you know how to write the equation of a parabola with a certain with a known vertex, then figuring out the vertex can help you to write it in that form. Okay, so two different ways to do that problem. Any questions on that? Okay, so how do I complete the square? What are the steps?
B over 2 squared.
Yeah, so take the b value. In this case, it's 6. Divide by 2, square it, add it, and subtract it. Okay, it's important to add it and subtract it, by the way, and not subtract it and add it. Just so you know. Okay, any other questions on this one? Just gotta open that. Okay, next question then, or next topic?
I have a question on, I don't know how to explain it. I'll zoom in very large. I think you'll be able to see it.
Yep, I can see it.
That thing.
Uh-huh, okay, that's a hard one.
I can't do it. My homework. Yeah, it's for the homework.
I redid this problem like 4 times.
Yeah.
There was one problem I redid like 5 times, and I was like, oh my god.
This is my 3rd time, and I'm like, okay, I'm done. Because this is my last problem.
Okay.
That's the biggest as Google makes me get. Probably hoping.
Okay, so
Should go any bigger than that.
we are gonna need 2 tools to do this problem. The first is just the standard theory of trigonometric equations. And the second tool we're going to need to use is this change of variable type argument that we've made a few times in class. Okay, so what's probably a good way to start this problem off?
Subtract the square root of 2.
Mm-hmm. And then divide by 2.
Yeah.
You agree with that? Okay, so we're going to reduce to sine of x minus pi over 2 is equal to the square root of negative square root of 2 over 2. Now, what I want to point out to you is that I think you would have an easier time doing a problem like this. Yes? You agree with me? That's an easier problem because you just need to think, well, if it gives me negative square root 2 over 2 for the height, okay, then it's probably like this angle or this angle, right? You see what I mean? I'm just thinking for a second. So, what do we want to say? We want, okay, this is true if t is equal to what? Let's do it. This is true if t is equal to this angle here or this angle here, where these are 45-90 triangles. So this angle would be the angle 5 pi over 4, right? And then the other angle would be the angle 7 pi over 4, right? Okay, so you would say, look, if sine of t is negative square root 2 over 2, then t needs to be what? T should be 5 pi over 4 plus 2 pi n, or 7 pi over 4 plus 2 pi n. Okay? Does that make sense so far? So what I want to think about here is, look, I want the input to look like this. Yeah? So let's just set them equal. What does it look like when I do that? It looks like x minus pi over 2 should be equal to 5 pi over 4 plus 2 pi n. Or x minus pi over 2 should be equal to 7 pi over 4 plus 2 pi n. Okay, so if we just add pi over 2 to both sides, we get that x should be equal to, so pi over 2 is 2 pi over 4, so this would be 7 pi over 4, or um, 9 pi over 4. Of course, 9 pi over 4 is coterminal to pi over 4, so probably I would rewrite this as not 9 pi over 4, but as pi over 4. Okay, so what is my game here? My game is to write down all of the solutions which are between 0 and 2 pi, and then I'm going to add 2 pi n to each of them, plus 2 pi n, plus 2 pi n. Okay, so if I was going to write down the solution set, it would be something like this. It would be x such that x is equal to 7 pi over 4 plus 2 pi n, n is in z, oops, union, x such that x equals 9, not 9, but just pi over 4, plus 2 pi n, n is in z. So let me show you what is going on here. Let me show you what is going on here by drawing a graph. So what does the graph of sine look like? It looks like this, yes? And then I'm just going to copy that and then paste it right there. And then I'm going to I wonder if I can like merge these. Group, there we go. Okay, and then I'm going to redraw my horizontal axis. Okay, so let me show you what's going on here. Sine of x minus pi over 2. It's the graph of sine, but we're moving it to the right by pi over 2 units. So you're looking for the intersections of this graph with the height square root 2 over 2. Okay? You know it happens at, sorry, negative square root 2 over 2. It needs to go down. What am I doing? Down here. So let's make this a little more nice. Here's pi over 2. Here is 3 pi over 2. And this is 2 pi. So you're looking for the intersections between the graph of sine and the height negative square root 2 over 2. And it happens at 2 spots here. The first one is 5 pi over 4, and then again at 7 pi over 4. Okay? So what are you doing when you're solving this equation? You're saying, well, I'm going to take this whole graph of sine, pick it up, and move it over to the right by pi over 2. Right? Move it to the right by pi over 2. So let's do that and see what kind of a picture we get. Well, if I take this whole thing and move it over pi over 2 units, you can see the location at which I'm going to have an intersection is going to change, right? You see that? So if I'm here, I touch here and here, right? Here and here. But if we pick the whole thing up and move it over to the right by pi over 2, then where am I touching? I'm touching here and here. Do you see the difference? So it's enough to say, look, I'm going to find out where are the intersections for sine. And I know that if I move all of sine just to the right, all the intersections are also going to move this same amount to the right. Does that make sense? I really want to know, like, you're not just nodding, right? Or are you just nodding, or?
I'm a little confused.
Little confused? Okay. How about you, Philly?
Yeah, I don't really know what to say.
Okay, that's good. I need that feedback, because then I need to go back and dig a little deeper here. So at the end of the day, we're looking for the x values such that if I plug it in here, or more accurately, if I plug it in here, subtract pi over 2 from it, then the output of the sine function is going to be this number. Loosely speaking, we can describe when is the output of the sine function going to be that number in terms of what is the angle input which is required. Of course, what we're trying to answer is a little bit more difficult of a question. It's not just what is the angle input which gives us this output. It's what is the angle such that if you turn it 1/4 of the way around the unit circle, you get an angle such that plugging it into the sine function gives you this number. Does that make more sense that way?
Definitely, yeah.
Okay. So at the end of the day, what do? We do this change of variable thing. We solve the easier problem first. We get the solutions to the easier problem, and then we say, look, I just have one little kink or wrinkle left to handle, and that's the fact that the input isn't just t, it's actually x minus pi over 2. So I'm going to set x minus pi over 2. That is going to be set equal to whatever are the inputs which are going to give us this respective output for sine. So I just set x minus pi over 2 equal to each of those things. And then I solve for x by the same way I would always do it, just move pi over 2 over to the other side. Okay? All right. Any more questions on this one? Does that help?
Yes.
Okay.
What section is the exam like gonna stop at? Like, is 5.6 and like 6.1 gonna be on the exam, or is it just stopping at 5.1?
I'm not going to put 5.6 and 6.1 on the exam. Well, the exam questions are going to come directly from the homework. So there's your answer. I mean, we hardly did anything in 5.6 and 6.1 anyways. We just kind of mentioned offhandedly that you can do trigonometry in bigger triangles, or that you can, the only thing that we did in 5.6 was like the sine 3x equals 1/2, which is a similar problem to what we just did. You do the change of variables thing. You solve when is sine t going to be 1/2, and then you set 3x equal to whatever those inputs are, and then you divide both sides by 3 instead of just adding pi over 2 to both sides. Other questions?
Can you do a problem similar to the first question of the remedial worksheet or whatever? The thing people can do in lieu of quiz 7.
Oh,
optional.
sure.
Can you do one that is similar to the first?
Mm-hmm. Let's do, let me see if I can find one. Because probably I'm not going to be able to make up a good one on the spot. Oh my god, why is the zoom so sensitive? I just want it to be a little bit bigger. Oh my god. Okay, right, we can work with this.
There's always command plus and command minus.
Oh yeah, that's true.
I had to make sure I was saying it right. It was on my Windows computer. I was like, wait, it's a controller for me.
Okay, let's do this one. 2 sine squared theta plus the square root of 3 sine theta is equal to 3. Okay? Does that one work for you? Okay. So, Randell or Sully, do you know how we can start off with this problem? Just looking for ideas or observations about this equation.
Do you get 3 on the other side?
Sure.
It doesn't? Shouldn't?
Do you use the double and half rule things for this?
And then you solve each one individually. Yeah, maybe. Is it that one? That type of problem?
So, let me address your comment first regarding the double and half angle formulas. I don't like that here, although I agree with you that maybe what's spurring you on to think of that is like, well, we got sine squared theta in here, that's annoying. Like, how am I, like, I'm not used to handling sine squared theta, it's kind of annoying, right? So you think like, well, just turn it into like a cosine. But the problem is, you're gonna then end up with an equation where you're gonna have multiple terms. Here you'll have something like 2 times like 1 minus cosine of 2 theta divided by 2, right? And then plus square root 3 sine theta, blah, 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 right? Minus 3 equals 0. Here's the problem with an equation like this. As much as you defeat the enemy of having a square trig function, you introduce a new enemy, which is that the angle inside of one of your trig functions is different than the angle inside of another trig function. That sort of thing, we don't really know how to handle trig functions with different angles on both sides. But there is something interesting about the structure of this equation. Okay, there's something interesting about the structure of this. It says 2 times something squared plus square root 3 of that something minus 3 is equal to 0. What kind of structure is that?
Quadratic.
It's quadratic. Specifically, it is quadratic in form, right? So the way that we want to solve something that is quadratic in form, if you remember, how did we solve equations which were like this? X to the 4 plus 2x squared plus 1 equals 0. Do you remember how we solved these ones? We said, well, if we make the change of variables y equals x squared, then we could rewrite this equation as y squared plus 2y plus 1 is equal to 0. You remember what I'm talking about now? Okay, so when we had this, what could we do? We could solve for y. We got y equals negative 1, right? And we solved this guy. And then finally, what do you have to do? You still need to, Okay, you still need to translate back, right? Using y equals x squared to then say, therefore, x squared equals negative 1 and no solution, right? Okay, so quadratic in form is when we have like some other, it's kind of like a composition of functions. We're taking one function, squaring it, and then adding 2 times just that function, and then add something else equals 0, and you solve it like a quadratic equation where you make this change of variables here. So in this case, the function which was being sort of composed here, the function which was being composed is the function x squared. For our example, the function which is being composed is just sine of theta. Okay, so you can rewrite this. If you say x or y or t or whatever is sine of theta, then how can I rewrite this equation in terms of x? What would it look like? Have a good one. What would it look like if I rewrote this equation by replacing, every time I see a sine theta, I'm going to write x instead?
Are you asking for the equation?
Yeah.
2x squared plus square root of 3x minus 3.
Is that what you got too? Okay. And you're just observing? Okay. That's
Can I
fine.
come out the corner now?
Yeah, of course.
I'm gonna reverse.
Okay, so so we translated this into x. What was the purpose of that? What was the purpose of translating this problem into x? Well, let's go back to this one. What did we do? We translated it into a quadratic equation so that we could then do what? Solve the quadratic equation. And then we are going to convert our solutions back into the original language. So what we need to do now that we have this quadratic equation is solve it. I need to find the x values such that if you plug them in here and here, this equation is true. How do I solve this kind of an equation? Well, this is a quadratic equation. We've got multiple tools for solving quadratic equations. Can somebody tell me one of the tools that we have?
Quadratic formula.
Yeah, quadratic formula. What's the other one that we can do sometimes? Factoring. We can do factoring and we can do quadratic formula. For this one, I think you're not going to have a good time trying to factor it. The reason is you have a square root of 3 in here. You're going to have to add two numbers together that get square root of 3. You're kind of doomed. Okay, anyways, so we're going to use the quadratic formula, which says x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So we do x is equal to negative square root 3 plus minus square root of 3. That's b squared is 3, because square root of 3 times square root of 3 is 3. Minus 4 times 2 times negative 3, all divided by 2a. 2 times, sorry, a is 2, so this is going to be 4. Yes? So now let's rewrite that a little bit better and say it's the square root of 3 plus minus the square root of, this becomes 3 minus negative 24, right? So I think that's 27, all divided by 4, which gives us the square root of 3 plus minus 3 square root of 3, all divided by 4, which gives us two solutions. The first one is x equals the square root of, x equals negative 2 square root 3 over 4, which would be negative square root 3 over 2. That's one solution. What's the other solution going to be? That was what I get when I subtract 3 square root 3. What's the other solution going to be? So we take square root of 3, and this time we're going to add 3 square root of 3. What do I get?
Is the first square root of 3 not supposed to have a negative? What happened to the negative? Like, the bottom of the first column says negative.
Oh, yeah. Sorry, I missed the negative. When I copied it back, I copied it incorrectly. Okay, so let's see here. We're actually going to get positive there, which is positive there. That's what I get when I add 3 square root of 3. Okay, so negative square root 3 plus 3 square root 3, we get 2 square root 3. Agree? It's like negative x plus 3x. We get 2x. And when I subtract, what am I going to get? Negative square root 3 minus 3 square root 3. What does that get me?
Negative 4 square root.
Yeah, negative 4 square root 3, right? Okay. So I get negative 4 square root 3 over 2. No, over 4. Which is negative square root of 3. Okay? So, I took this problem and I translated it into a different language and I solved the problem in the different language. What's left still to do?
Switch it back to solving.
We want to go back to the original language. So, now we're going to get two new equations. Remember, sine of theta was x. And x is one of these two things. So we need to solve two equations. The first one is sine of theta equals root 3 over 2. The second equation is sine of theta is equal to negative square root of 3. But I claim that you only have to do one of them. Why do I only have to do one of these?
Like if square root of 3 is bigger than the radius of the circle.
Yeah, this is not possible. There's no angles which will produce this output for sine because the output of sine is always between negative 1 and 1. This number is outside of the range of the function, so I'm not going to worry about that. I am going to worry about the first one, though. So how do I do this one? I need to find all of the angles theta such that if you plug them into sine, I get this as an output. This part I hope we feel a little more confident in doing. Can someone help me out? How am I going to do that? Sine of theta equals square root 3 over 2. So this is...
Triangles.
Okay, do some triangles. Why don't we start by drawing a unit circle. Okay, I have a unit circle now. What else should I draw?
Make like the triangle and do the right angle formulas to do it. Like if you have y's or square root of 3 over 2, then you can do the right angle formulas.
Yes. So, I'm looking to put some angles in here, right? I want to put some angles in here, but I want to draw them in a nice way that looks like how they're going to look in the end, right? So the question is, what, do I put an angle down here? Do I put an angle here? Do I put an angle here? Do I put an angle here? Where should I draw my angles? Well, this number tells us something about where we are on the unit circle. What does it tell us about where we are on the unit circle?
It's on the top half.
Top half of the unit circle, right? Because this is sine we're talking about here, which means we're talking about the y value. So we're looking for a point on the unit circle whose y value is that number. How many are there?
Two.
There's 2. So here's the y value that we want. You can see there's 2 points who have that height, yes? So there's one here and then one over here. And now, like Sully said, we're going to draw some triangles. Here's my first triangle. And then here is my second triangle. Okay? So now what am I supposed to do? I'm supposed to figure out the angle. I have the triangle, I have the point, I know the x, actually I know the y value. How do I figure out the x values of these coordinates?
You can do like 30, 60, 90 right angles.
That's true. Or I could use the Pythagorean theorem. Okay, so let me show you how you would do it using the Pythagorean theorem. We already decided we don't need to do that, so I'm going to get rid of that. Pythagorean theorem says what? X squared plus y squared is equal to 1, right? We want to know what x is. We know that y is square root 3 over 2. So x squared plus square root 3 over 2 squared is equal to 1. So x squared plus 3/4 is equal to 1. So x squared is equal to 1/4. And therefore x is equal to what? Plus or minus 1/2. But yes. So here's the one where it's 1/2, and here's the one where it's negative 1/2. Okay? So I personally like finding the x value and the y value of these points first so that you can tell what kind of angle this is by looking at this. You see, this is square root 3 over 2. This is 1/2. This is 1. What is this angle then? 60. And this angle's 30. Do you see how I got that, Caroline?
I do.
Okay. So I got that because I put the smallest angle across from the smallest side, biggest middle angle across from the middle side, and then of course the 90-degree angle is the biggest angle, which is why it's across from the biggest side. Okay, so now I have figured out the angles, right? Well, that's a 60-degree angle. We also know that this is a 60-degree angle. So what I'm supposed to do is describe the angles theta such that you get a point on the unit circle whose height is root 3 over 2. I've done so. The first angle is 60 degrees or pi over 3. So theta could be pi over 3. That represents this angle. What else could theta be? What's the other angle? What's this angle shown in red here?
2 pi over 3?
Yeah, it's 2 pi over 3. How did you get that?
Just intuition.
Just intuition. Well, I think it has something to do with the fact that you know this angle is pi over 3. Yeah, so, and you know, look, pointing straight to the left is pi, and I need to do pi over 3 less than that. Okay, so that's how I like to think about it in order to get 2 pi over 3. Because this would be 3 pi over 3 is pointing straight to the left. And I need pi over 3 less than that, which is minus pi over 3 from this, so that's how you get 2 pi over 3. And am I done? Have I found all the angles which cause sine of theta to be root 3 over 2?
Yeah.
No.
No? Wait, what? Wait.
Let me show you another angle.
Well, yeah.
And another one.
So
And another one.
Whatever it's called, it's like a range of, what do you call it?
It's like a
Notation.
These are notation.
set builder notation. Yes, I need to use set builder notation. So I can take any of these angles or any of these angles plus any multiple of 2 pi. Okay? So if you want to use set builder notation, you'd say like this: theta such that theta is equal to pi over 3 plus 2 pi n. N is an integer. Union. Same freaking thing. But 2 pi over 3. Okay? Now I'm done. So, let's review this one slowly. The first thing to notice is that this equation is quadratic in form. Actually, the first thing to notice before that is to move everything to one side. But I would argue that moving everything to one side is kind of like, I would already be doing that with the recognition that this is quadratic in form, because when you have a quadratic, you move everything to one side in order to solve it using the quadratic formula. So noticing this sine squared, sine, and then nothing, it's like, okay, it's quadratic in form. Then we need to do our change of variables. So let x be whatever is the function which is getting squared, okay? And then you rewrite the equation in terms of x. You solve the equation in terms of x using tools which you have known for quite some time now. We even learned them in our class, the quadratic formula. And then you get two solutions for x, as you might expect from a quadratic. Then you have to translate back. You know what x is now, and you know that x is sine theta. So you set sine theta equal to the two numbers which you got for x. In this case, one of them we can just immediately eliminate. The reason we can immediately eliminate this one is because sine theta is never going to be negative square root of 3 because that number is too big. Sine theta can't produce this kind of output. It can produce this kind of an output. And to see what inputs will cause this output, we need to ask ourselves, what is the output of the sine function? The output of the sine function is the y value of a point on the unit circle. So what I'm looking for is an angle theta which points at a point on the unit circle whose y value is square root 3 over 2. Once you know that, you can draw the 2 points. There's 1 and then 2, right? You can see them. And then you can draw some triangles. You can use the Pythagorean theorem to solve for the other side length. Since you know that the one side length is square root 3 over 2, you know the other side length is 1, you can get the final side length using the Pythagorean theorem. Once you have the lengths of the sides of this triangle, you can determine that this is a 30, 60, 90 triangle and determine where does the 60 and 30 go. Finally, you're ready to describe the angles theta, which cause us to be at either this point or this point. It's pi over 3 or 2 pi over 3. Or either of those angles plus any multiple of 2 pi. Or minus any multiple of 2 pi. Okay? So that's the full story of a quadratic in form type trigonometric equation. Are there any questions about this?
Will it be in the exam?
People always want to ask me these sorts of things. Is it on the homework?
Yeah. I haven't been able. This is 5.1 stuff, right?
This is 5.5.
This is 5.5?
Yeah.
Well, we're not doing much 5.5.
If it's on the homework, it's possible that it shows up on the exam. That's all I can say.
So the regular exam, like, how many questions? Like, how much is our exam?
I think I did like 9 questions on each exam, right? 3 pages, 3 questions on each page.
So what, like 13, 14? Like,
We'll have like, yeah, like either 12 or 15, somewhere in that range.
So, like one question from each unit, maybe?
No, I'm not gonna be able to. We did too many units, I think. I don't think I can do that. I can do like, I would think about it in terms of chapters, right? Because you have 5 chapters, so probably like 3 questions from each chapter, something like that would be more accurate.
That's on Monday next week, right?
Huh?
It's on Monday next week.
Tuesday.
Why?
At least I'm pretty sure it's on Tuesday.
This is my only in-person
Sorry.
I only have 2 exams. I have 1 in-person, 1 online for some reason. It's because I have a final paper for history instead of an exam. Honestly worse.
Yeah, I hate final
It's 10
papers.
pages. 10 to 12 pages. And it's a research paper.
What?
Bar.
It's history 112.
Oh, no, wait, is that American history?
Mm-hmm.
I was
Civil War.
Listen to this BS. So I have to take a non-US history next semester. I got stuck in a 300 level history course. History of the Byzantine Empire, 4th to 11th centuries.
Wow.
That's kind of freaking awesome, though.
I mean, it kind of is, but
I'm
I'm not
just
psyched about
saying.
that term paper.
It's going to
Like,
be more entertaining than U.S. history.
I had to Google what the Byzantine Empire was.
Let's
see how that class will go.
But then you're gonna have like such hyper specialized knowledge, and like you'll be watching Jeopardy in like 30 years, and you'll know the answer to one of the questions. You'll be like, hell yeah.
That's what the classes are for, right? Like, what? Who does that? Who teaches that?
A
It's
historian.
for Jeopardy, man. That's what it's gotta be
We
for.
could never be
Who
a
needs that
historian.
knowledge?
I'd be so bored.
They're taking your money.
A lot of history majors go on to do law school. That's what I am aware of. So I mean, I think it's useful in the sense that like you learn the like past mistakes of civilizations so that you don't repeat them.
It must be important. I've never heard of it though. Never.
Well, anyways, I only took one history class when I was in my undergrad. And actually, it wasn't in the history department. It was in the philosophy department. It was history of, like ancient Greek philosophy. That class kicked my ass. That was really bad.
I feel like it's more applicable though, You get a little bit of philosophy knowledge. Basically just anything you ask.
Yeah, but like it was really hard actually because I was used to like philosophy classes. I was a philosophy minor, so like I was used to like the idea of like modern philosophy and going back to like ancient philosophy, they were like it was really hard for me to get my head around because there's so much like stuff that like they laid the groundwork for that like nowadays we just take for granted in terms of like what things are, what is the idea of a concept. And that like when you go back to first principles and say I'm gonna like not agree upon like what even is an idea, then it's like I don't know, it feels like so like you can't say anything about anything without like the common understanding of like what the notion of what the basics are exactly. So that was hard, but
Sounds terrible.
it was interesting.
Yeah.
Anyways, should we do something else?
Yeah, sure. You have any questions? I don't know what to ask, honestly.
So you got it. You got it.
Actually, on the quiz, I can't do it anymore. There was Pythagoras Identities and stuff.
Mhm.
The third question I had no clue what was happening. And that was the big points question, so I'd like to go over it.
Okay, you want to go over the quiz problem?
Yeah. It's just Pythagoras Identities, but I don't know those yet, so I assume they'll make a lot more sense once I know those.
Okay, so then let's in greater detail go over the Pythagorean identities.
Have you already been over that since you've been here? Well,
No.
I don't think I'll go over it again. I can do that one time.
No, we should go over it
Alright.
for everyone's benefit. And then we'll do this problem. Okay, so the first thing is to say something very simple. So Pythagorean identities, they're going to be relationships between the trigonometric functions, which have something to do with Pythagoras makes us think triangle. Okay? In fact, Pythagoras makes us think a squared plus b squared equals c squared, right? So the big one is that, look, if you have a unit circle, and you take a look at a point on the unit circle. So let's actually put an angle in here. And just for the hell of it, let's draw it over here this time, for no good reason. Here's an angle theta. You know that this point has coordinates. The coordinates are given by cosine of theta and sine of theta, yes? Do we agree on this so far?
Yes. Sorry. This is a little delayed.
It would have been kind of funny if you said no, though. I don't know what I would have said.
Well, I was kind of zoning out for a second there.
No, that's okay.
I
So
had to catch up.
we put in theta, the angle. It points at a point on the unit circle.
Yes.
The x value of this represents this length here. That's what we get for cosine theta. And then the y value is the height. That's sine theta. Yes? So in particular, okay, cosine theta is describing this length here. Yep, that length. And sine theta is describing this length here. And what is this length?
Oh, man. I thought I remembered.
Was it which one? The red?
The red, yes. I'll give you a hint.
Would it be?
This goes from the center of the unit circle to the outside of the unit circle.
Radius?
How far is that?
Well, wouldn't, like,
1, right? The radius of the unit circle is 1.
wait, so it's 1?
So this is 1.
Oh, that was. I should have said that. I knew that.
So that's 1. Okay. So what does the Pythagorean theorem say? It says a squared plus b squared equals c squared, where c is the length of the hypotenuse. A is the length of one of the legs, and b is the length of another one of the legs, the other leg, right? So what is the length of the first leg? Let's say this leg. It's whatever this number is, yeah?
Mhm.
So cosine of theta squared plus the length of this leg squared, which would be sine of theta squared, should be equal to what?
1.
1 squared, which is 1. So this gives us our first Pythagorean identity. Sine squared of theta plus cosine squared of theta is equal to 1.
So we're looking at the triangle identities.
Yeah, exactly.
Cool.
And there's more triangles we can draw, which probably you don't remember this, but we did this at some point, where we said, look, here's the tangent line or whatever,
Yeah.
and it comes down like so, and then you can make another couple of triangles. One of them is this triangle, yes, and then another triangle you can look at is this triangle here. And these lengths of the sides of these triangles are like tangent, cotangent, secant, and cosecant, okay? So you're gonna get basically more Pythagorean identities from those triangles, which you can derive geometrically if you prefer to do it that way, but I think it's kind of hard to remember. So what I recommend you to do is just remember this one, and remember the following. To get the other two, you're gonna divide everything by this or by this, okay? So let's see what happens if we take the whole thing and divide by sine squared theta. So this is number 1. 2, we're gonna divide both sides by sine squared theta. We're gonna get sine squared over sine squared is 1, plus, now cosine squared over sine squared, what's that gonna give me? Cotangent squared. And then 1 over sine squared, what does that give us?
Cosecant squared.
Cosecant squared. Okay? To get the third one, I'm going to take the first equation and divide both sides not by sine squared theta, but I'm going to divide by cosine squared theta. So divide both sides by cosine squared theta. Sine squared over cosine squared is going to be what?
Tangent.
Squared. Yes. So you get tan squared theta plus cosine squared over cosine squared. 1 over cosine squared.
Yeah.
Secant squared theta. Okay. So these are the 3 Pythagorean identities. Okay? So, one thing that I want to mention about the Pythagorean identities is, look, the angle inside on both sides has to be the same. Okay? It's not going to be true if you're saying, well, the side of this, if you say, well, the side of this triangle and then the length of like some other triangle, they may not be related in any kind of way, as long if the angles are different. But if the angles are the same, we're talking about the same triangle, same sides of the same triangle, all add up using this Pythagorean theorem. Okay? So that's Pythagorean identities. Let's see how that helps us on the quiz problem, which was sine squared of pi over 8 plus cosine squared of pi over 8 plus cotangent squared of pi over 3. In light of what we just learned, Lawson, what is this?
A Pythagoras identity, almost.
Almost.
Well, let me see him. I forgot him already. Go scroll below.
That's why I scrolled down, so that
It's
you
not fair. Let me see him.
Okay,
It
but
equals 1 though. It equals 1.
exactly.
So
Okay.
wait, I can just put 1 there.
Yeah, you can rewrite this
Wow.
as look.
See,
This is 1.
I knew it was gonna be super easy. Like as soon as you start trying to do it. And then that's another Pythagoras identity, isn't
Yeah, what's this one equal to?
it? Like secant or something. Cosecant.
The way you can remember it is, actually, I don't even want to say that. You just rederive it. Rederive it, actually. I almost said something sacrilegious, but this is going to be cosecant. Okay, tangent goes with secant.
Okay.
Cotangent goes with cosecant. But I didn't want to say that co goes with co, because in the case of the reciprocal identity, 1 over cosine does not equal cosecant, right? It's cosine secant.
Whatever, right.
Okay, anyways, this is cosecant squared of pi over 3. Am I done?
Well, you have to find that.
You have to find
Why
that.
is it squared? What are we gonna do if it's squared? This was.
Good question. Do you know how to do it when it's squared? Is that going to cause a problem?
You just.
Would you know how to do it if there was no 2 here?
Yeah.
How about if there is a 2 there?
I'm gonna assume you just square. Once you find what cosecant is, you just square that. Which is what I did on
Exactly.
paper, though.
Yeah, this is
I was wrong.
just cosecant of pi over 3, which you said you already know how to do. Square, and you know how to square stuff.
Ugh.
Okay, so how do I do it? How do I do cosecant of pi over 3?
Well, you can do the whole triangle thing.
Mm-hmm.
Also, the things for pi over 3 is just 1/2, and then square root of 3.
Yes, that's true. They are going to be those numbers, but I think the number one thing you want to do before you do anything else when you're doing a trig problem like this is draw a picture. Okay, draw a picture. So draw a unit circle. So here's our unit circle. And then what do we want to do with the unit circle? We want to put in the angle. What kind of angle is pi over 3? What does it look like? Is it over here? Is it over here? Where is it?
It's like the last.
It's the only one you didn't do.
It's in the first quadrant. Okay, and is it like an angle like this or an angle like this or
The ladder.
the second one? Okay, yeah. What we want to remember is, look, pi over 3 is like 60 degrees. 60 degrees is more than 45, so 45 would be pointing halfway, but 60 is more than that, so it's like up here
That
somewhere.
was cool. What you just did there. How do you do that? It wasn't like attached to the circle.
A magician never reveals his secrets. No, it's because, okay, if you draw a line and then you hold, it will like flatten out the line, and then if you like move it, it can like move it. So I was just doing that. It just looked cool because it was inside of the unit circle here, and I was like, you thought it was like all connected already, but it's not. It's just that I'm like,
That was cool looking. Yeah.
anyways.
You can do that in class. Show off the kids.
I do that in class like all the time. You're
It's in
just
the morning. I don't really. I'm zoning.
Okay, anyways. 60, 30. This point has what coordinates?
1/2 square root of 3 over 2.
Good. Okay, so cosecant is what? It's got to do with this x and y value, doesn't it? What should I do with the x and y value? Divide x by y, okay? Actually, no.
It wasn't 1 over something?
Oh, wait, no, I was thinking cotangent.
We're doing cosecant here, which is 1 over
Why?
sine, which is 1 over y, yes.
Wait, that
You're
way?
correct, yeah, you're correct. 1 over y. Okay, so we take 1 over 2 what am I doing? 1 over 1/2, which is 2. And then we square it, and we get...
It's 1 over.
What am I doing? Am I doing something wrong?
It's square root of 3 over 2.
Oh, what am I... Yeah, okay, sorry. Okay, so thank you. I was like, this doesn't seem right for some reason. Okay, so it's 1 over the square root of 3 over 2 squared, which is 2 over the square root of 3 squared, which is 4 thirds. Now I did it right.
Sweet. That wasn't that bad. It's unfortunate. I was like sitting over there trying to think super deep on it. You just did that right away. I can't believe half the equation. That was the hard part. I was like, what is it, pi over 8? We don't ever do pi over 8.
Well, exactly. So if you see something like that on the exam, you know, or on a quiz or on the homework or whatever, you should have like alarm bells going off in your head where you're like, what the hell? Pi over 8?
Yeah.
Like, I can't do pi over 8 unless you had a calculator, but you're not going to be able to have a calculator, so you don't know how to do pi over 8. So
Pythagoras Identities.
that kind of leads you to think like, yeah, what else can I do here to rewrite this? Of course, you actually can do sine squared of pi over 8 now that you've seen section 5.3. Do you know how I would actually compute sine of pi over 8? Sine squared of pi over 8? How would I do something like that?
Do the adding and or like the add. What is it? What are they called? What are those formulas called?
Sum and difference formulas? Okay, yes, you could do one of those and then get whatever is sine of pi over 8 and then square that. There's one other thing we can do which is even easier than that.
Double.
Yeah, if this was pi over 4, you would know how to do it, right? Which pi over 4 is double pi over 8. This is the same as 1 minus cosine of 2 times pi over 8 all over 2, which is 1 minus cosine of pi over 4 all over 2, which is 1 minus the square root of 2 over 2, which is like 1/2 minus the square root of 2 over 4, something like that. Or if you want 2 minus the square root of 2 all over 4, that could work too. Anyways, you know how to do cosine of pi over 4, that much I believe.
I'm supposed to know how to do that. That at the end there? Wait, why is it equal to 1 minus cosine times 2? I know that get the whole like pi over 4 twice as, or double.
So your question is about this equality, how we go from here to here?
Yeah, why is there 1 there now? Am I missing something?
That's the...
Oh, Pythagorean identity.
No, it's not the Pythagorean identity. It's one of the double or half angle formulas. I can never keep them straight which one it is in terms of the name. But this is one of the things we learned in class in 5.3. Let me see if I can find it. So this would have been on like maybe Monday of last week, double and half angle formulas.
Oh, I need to catch up.
Okay, so actually I didn't prove these in class. You can prove them using various, I don't remember exactly how they're proven, but you can draw some triangles and shit and prove it. But what I wanted you to know is that it's true and it's really important for calculus because you can reduce the power, okay? So these are really important because sine squared suddenly becomes cosine of something. And having a 2 on the inside here is way better than having a square on the outside when it comes to calculus. So you could do this one of two ways. You could use the half angle formulas here, or if you wanted to do you could use sine of pi over 8. You can rewrite using one of these. You could say, well, pi over 8, see if I don't get this wrong, is just what? Can I write it as a difference? No, I don't think I can. Can I? Okay, let's think about it. If I have pi over 2, pi over 3, pi over 4, pi over 6, is there a way to subtract one of these from the other and get pi over 8? I don't think so. Pi over 4 minus pi over 6 would be pi over... No, that would be... Jesus, why is this so hard? It'd be 2 pi over 24, pi over 12. Yeah, no, there's no way that I don't know what I'm thinking. I'm just tripping out. You could do you can do sine of pi over 8 using the double angle formula or the half angle formula, whichever one it is. I don't remember. You can do it like that.
I don't have any other questions, honestly.
But in this problem, it's easier if you just recognize that, the angle's the same inside both of those, and also, whatever it is, it's going to be annoying as all get out to try to do it. So using this Pythagorean identity makes things a lot easier. You replace two things which were going to be a pain in the butt to solve with one. That's a good trade. Okay?
Yeah, we're starting to do that. Very useful.
All right, let's do something else. What's up next? Okay. Anything else y'all want to study, or you want me to come up with something? I'm not going to tell you what's on the exam, but we can study whatever you whatever you want me to pick. I mean, all of it is important. So, I mean, what are y'all thinking? Let's take a look at the assignments, maybe, and I'll tell you. We'll look at the assignments and see. So nothing from A. Okay, how about, let's see, parallel and perpendicular lines. We got functions, properties of functions, transformations of functions, combining functions, plugging functions into other functions, quadratic functions. Have I hit on any soft spots yet? Okay, I'll keep...
Yeah.
Oh.
Yeah, can you go through quadratic functions real quick?
Mm-hmm.
I really forgot what that meant.
Quadratic means something like x squared plus 2x plus 1 equals 0. Solving using factoring, solving using grouping, solving using quadratic formula, vertex form, completing the square, stuff like that.
Those last few, completing the square and vertex form, I don't know what that means.
Okay, we talked about that at the start of this class, so watch the recording.
Like the very start,
I mean, like, while you were doing your quiz, yeah, we were talking about that. So I'm just gonna direct you to the recording to study that instead of doing it again.
Yeah.
Polynomials, rational functions. Remember when we divided polynomials by polynomials? Graphing those was kind of tricky. Doing inequalities with those was kind of tricky.
Which one was the one with asymptotes?
Rational functions.
Will you do one of those?
Yeah, sure.
Oblique asymptotes.
We didn't talk about oblique asymptotes.
I was gonna say, I have no idea what that is.
Here we go. Okay, maybe let's do something really simple first. Let's do something really simple, like this function. I'm gonna change the screen in a second. Okay, let's take a look at these two functions. And let's graph them. Okay, so the deal with these types of functions, right, is we have to be really careful about what we plug in, because there's a chance I can make something go very horribly wrong. How can I make something go very horribly wrong with this function?
If you plugged in 2.
If I plug in 2, what's going to happen, Lawson?
Plug
Into this equation, if I plug in 2, what will happen?
it would be undefined.
Yeah, be 1 divided by 0. So that's how I can make something very bad happen with this function. So we know that when x is 2, something bad is happening. In fact, we can't even graph the function when x is 2. It's undefined. But what about when x is very close to 2? Okay? Well, this is a question about limits, okay? So we sort of waved our hands at something called limits, which we said, look, limit as x approaches 2 from the left. We write like this, 2 with a minus sign to say from the left, of f of x. And we ask ourselves, if we take numbers which are close to 2, but less than 2, and plug them in, what sort of outputs do I get? So let's do a quick test. If I plug in something like, okay, let's plug in x and then f of x. Okay, if I plug in like 1.9, what do I get? I get 1 divided by negative 0.1, which would be negative 10. If I plug in 1.99, what do I get? I get 1 over 1.99 minus 2, which would be 1 divided by negative 0.01. Right? You know what this number is?
Really big.
Well, it's big, yeah. You can be more specific, though. This is 1 divided by, this is 1/100th. So negative 1 over 100. Dividing by 1/100th is the same as multiplying by what? 100 over 1. So dividing by really small numbers is the same as multiplying by really big numbers, right? So I get, sorry, negative, and then so negative 100. Okay, how about 1.999? You know what I'm going to get?
Probably 1,000.
Yeah, negative 1,000. And then 1.99999. Okay, blah, blah, blah. You get the point. So, as the x value creeps closer and closer and closer to 2, you notice that the height of the function is like going down, 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 right? So this is telling you that we have like an asymptote type of behavior. And the big deal with the asymptotes is to figure out what they look like. And there's basically a couple of options, okay? Here's option number 1. Boom and boom, right? That's one option. We know that's not us, right? Because we know on the left side we're going down, right? So ours is definitely going to look like this on this side. But now we also need to figure out what it looks like on the other side, right? To determine whether it looks, so it's going to, these are the options. Here's option 1. Option 2 would look like this, yeah? Option 3 would look like, would look like this. And then option 4 would look like down and down, right? So it's either up, down on the left or up, down on the right. Whatever combinations you can make thereof, right, is what we could get. So now let's try from the right, okay? What happens when we go from the right? So let's do limit x goes to 2 from the right of f of x. And we're going to replicate this table, okay? The only difference is this time x is going to be approaching from the right. That means we're going to take x values which are very close to 2 but larger than 2, okay? So we're going to march from the right like so. Getting close to 2 from above. So we're going to consider inputs which look like 2.1, 2.01, 2.001, blah, 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 right? Get the idea? So what happens when I do 2.1? I get 1 divided by 2.1 minus 2. That's 1 divided by 0.1, which is what? Divide by a tenth is the same as multiplying by 10. So I get 10. How about 2.01? What am I going to get?
100.
100. And 2.001?
1,000.
1,000. What kind of behavior am I seeing on the right side? As the x value gets closer and closer to 2, the height of the function is doing what?
Rising.
It's blowing up, right? Okay, so this tells us that this function is going to look like so. Make sense? So, asymptotes are about figuring out what's going on with this process. Now, we had some shortcuts, which we talked about in class, where we said, well, you look at the sign of the leftovers and then the multiplicity of the 0 in the denominator. Loosely speaking, if we have a 0 of an even multiplicity, it's going to be like a same behavior, either up, or down. If you have an odd multiplicity, like 1 or 3 or 5, then you're going to have opposite behavior on both sides, like we see here. But it might look instead like this. Okay, it might look instead like that. But generally speaking, that's the type of behavior you're going to have. But if you want to know for sure, you can always do this process, right? Plug in numbers which are slightly to the left and getting closer. Plug in numbers which are slightly to the right and getting closer. And see what happens to the value of the function as you go along. Okay? So let's take a look at the other one. After you get a hang of this, okay, you can sort of do these limits without actually having to do this plugging stuff. Let me show you what I mean. So for g of x, 1 over x minus 2 squared. First of all, I know that it's going to have same behavior on both sides. It's either up, or down, because it's an even multiplicity 0. But second of all, I know it's going to have an asymptote at 2, because 2 minus 2 is 0. Now, what's happening when x gets very close to 2? Okay, when it's very close to 2 and less than 2, the denominator is going to be, this will be a negative number, but then you're going to square it, and it'll become positive. So it'll be something on the top, which is 1, positive, divided by something on the bottom, which is positive and small. Okay? Divide a positive number by a very small positive number, you get a very big positive number as a result. Okay? So this is going to like plus infinity on this side. Now let's try again on the other side. Well, it's going to be the same. In fact, this is an even function. So it's going to be symmetric about, it's not an even function, excuse me. It has a symmetry, is what I mean to say. It's a transformation of an odd function. Or sorry, it's a transformation of an even function. This is x to the minus 2, which is an even function. Move it over to the right 2 units. Still going to have a symmetry. It's just moved to the right. So it's going to look like this. Okay? So, like, you can sort of visualize, like, well, when x is getting very close to 2, this number is becoming very small. Whether it's negative or positive is neither here nor there, because I'm going to square it anyway. And it'll become positive if it was negative. Or it'll stay positive if it was positive. So you imagine, like, okay, if I take a number like 1 and divide it by something positive and very small, okay, then this is going to give you a number which is positive, because the top's positive, bottom's positive, and it's going to be big by virtue of having a very small number in the denominator. Okay, remember what I mean. When I take 1 and I divide it by something like 0.000001, this is the same as doing 1 divided by, let's see, this is the tens place, hundreds, thousands, 10,000s, 100,000s, millionth. This is the same as doing 1 divided by 1/1,000,000th. It's 10,000, 100,000, there we go. See what I mean? 1 divided by 1 over a million is the same as 1 times 1,000,000. So dividing something by a super small number is the same as multiplying by a super big number. Okay? Okay, is this helping so far? How do we feel about that? Okay, so let me go back to chapter, what was this? Was this chapter 2 that we did this in?
No. The homework thing that you were on said 2.4.
2.4? Okay, thanks. That might be too far. Oh, that's 2.3. Okay, here we go. 2.4. Okay, so rational functions. So let's just review some of the notes really quickly, and I'll say some things about this. Okay, so we said, look, our function's going to have a vertical asymptote anytime the denominator has a 0, okay, basically, as long as the numerator is not 0. We're going to have some kind of this type of behavior at a, okay? So if the limit as x goes to a from the left is plus or minus infinity, or if the limit as x goes to the right, goes from the right, sorry, of f of x is plus or minus infinity, then we have an asymptote. Okay, so when are we going to have one? We're going to have one when x equals a is a root of the denominator and not a root of the numerator. Jesus, I almost just broke my iPad screen from emphasizing that so much. Okay, so it should be a root of the denominator, but not a root of the numerator, okay? If it's a root of both, then we have a whole. Okay, so let's see a quick example of that, like this one, okay? X plus 3 times x minus 3 over x plus 3. X equals negative 3 is not in the domain, so we're going to have a whole. Otherwise, you can cancel x plus 3 with x plus 3 and just get x minus 3. So other than this one point, the function's going to look like x minus 3. Y equals x minus 3, except for at this one point. Okay, if we do have a 0 in the denominator, which is not a 0 of the numerator, then we need to check the behavior on both sides. We check the behavior on both sides using this limit process, where we say take number which is really close but smaller. Take a number which is really close but bigger, and then see what the height of the function is. If it's getting really huge and positive or huge and negative, that tells you how to draw the asymptote. All right. Okay, there was a lot of other stuff in here, right? Like, when are we going to have horizontal asymptotes? Well, we care about the power, the biggest power in the top and the biggest power in the denominator. Depending on which one is bigger, we might have no horizontal asymptotes, we might have 0 as a horizontal asymptote, or we might have the ratio of those two terms. Okay, the ratio of those two terms, if we have equal sign in the top and bottom. Okay, so maybe we can talk more about rational functions in class tomorrow, because there's a lot more to say, but maybe we'll talk about that tomorrow. Does that sound good?
Do we have time?
Huh?
Are we out of time?
Yes, 3:58.
Ah.
I mean, do you have something quick you want to talk about? We can do that.
Take your email. I'm good. I ran out of things to talk about.
Okay.
I need to watch those lectures because I hadn't watched the last two. So.
Yeah, watch the lectures, and also, you know, next time, if you come with questions already prepared, then you won't ever run out of questions.
I'm surprised when people aren't here right now, honestly.
I'm
There's a
kind
Thursday
of surprised
one.
too. Yeah, there's a Thursday one. There will be a lot of people on Thursday, I think.
Guys, that's for school.
Yeah.
All my classes got canceled today and yesterday except math for some reason. So I was like,
Really?
why would I not come to office hours? I had nothing else to do today.
All of them got canceled? Why?
Yeah, I was supposed to have